this session, Pablo Tecaria from Universidad Nacional de La Plata, and he is going to talk about minimal vertex separators and new characterizations for dual chordal graphs.
Well, in this talk I am going to speak about dual chordal graphs and especially about the minimal vertex separator. Many characterizations and properties of dual chordal graphs resulting from about 30 years of research. But as far as I know, nothing or very little has been revealed about minimal separators of dual chordal graphs. For that reason, one of the main purposes of the paper was to try to fill that gap. Well, I am going to start with some quick definitions of the concepts involved in this presentation. I would also like to add that whenever a graph G is mentioned, it will be assumed to be connected because many of the properties that we are going to see can be reduced easily for disconnected graphs. They are known to be true for connected graphs. Well, given a graph G and two non-adjacent vertices U and V, a UV separator will be a set S of vertices of G such that G minus S is disconnected and U and V are in two different connected components of G minus S. That separator is minimal if no smaller subset has the property of separating U and V. And we will use the notation S of G to denote the family of minimal vertex separators of G. We say that a complete is a set of pairwise adjacent vertices and that clique is a maximal complete in the sense of inclusion. And C of G is used to indicate the family of cliques of G. We say that a family of sets is L if the intersection of all the elements of any family of pairwise intersecting sets is not empty. And in the particular case that C of G is a heavy family, we say that G is a heavy graph. Well, a chord of a cycle is defined as an edge showing non-consecutive vertices of the cycle, and chordal graphs are defined as those graphs without chordal cycles of length at least 4. Other graphs that we consider are intersection graphs. Given a family F of sets, the intersection graph of F or L of F has the sets of F as vertices, and two of these sets are adjacent if and only if their intersection is not empty. Here is an example of an intersection graph where the family is composed of the sets whose elements are 1, 2, 3, 1, 3, 1, 2, and 2, 3. And we refer in particular as clique graph to the intersection graph of C of G. And generally we use K of G for the clique graph. Well, now I introduce dual chordal graphs. Given a graph G, we say that a vertex W is a maximum neighbor of V if the set of vertices at distance at most 2 from V is contained in the neighborhood of W. And an order V1, V2 to Vn of all the vertices of G is a maximum neighborhood ordering of G if for each I, Vi has a maximum neighbor in the subgraph induced by Vi and the following vertices of the order. And finally, we call dual chordal graphs to those graphs which have a maximum neighborhood ordering. That would be an example of a dual chordal graph. In color, we have all the vertices at a distance at most 2 from 1, and we can see that they are in the neighborhood of 2. So 2 is a maximum neighbor of 1. And similarly, we consider the subgraph induced by all the vertices except 1 5 is a maximum neighbor of 7. And if we continue like this, we will be able to get a maximum neighborhood order. But this is not the only way to define dually chordal graph, as there are many other characterizations. One of them says that the graph is dually chordal if there exists a spanning tree P such that each tree induces a subtree. And a similar version says that a graph is dually chordal if and only if there exists a spanning tree such that every neighborhood induces a subtree. Any of the trees satisfying any one of those two characteristics are the same, so we call them compatible trees. And this gives us a new way to prove that the graph of the example is dually chordal. We take the spanning tree at right, and the blue curves indicate the subtrees that the cliques induce. And there are even more characterizations. In fact, she is dually chordal if and only if she is hairy and K of T is chordal. And also, G is dually chordal if and only if it is the clique graph of a chordal graph. If we consider again the graph of the example, it can be found to be the clique graph of the chordal graph at left. Well, now we will try to relate separators and neighborhood of vertices of dually chordal graphs. One of the classical characterizations of chordal graph says that a graph is chordal if and only if each minimal separator is a complete. That could be interpreted as the vertices of the minimal separator being very close to each other. So it could be interesting to wonder how close to each other the vertices of separators of dually chordal graphs are. And one way to find out is to determine if they are contained in a neighborhood. What we can see first is that if we have two vertices U and B non-adjacent, then there is a different vertex W such that its neighborhood except U and B is a UV separator. So if it contains a UV separator, it will also contain a minimal UV separator. To prove it, we just need to take a compatible tree and let W be an inner vertex of the path in T from U to B. For example, this graph is dually chordal and the color edges determine a compatible tree. There, 7 and 4 are not adjacent and 8 is between them. And we can see that the neighborhood of 8 minus 7 and 4 separates 7 and 4. This separator is not minimal, but we can make it minimal if we remove some vertices. But this does not mean that all the minimal vertex separators are contained in a neighborhood. In fact, 1, 7, 8, and 4 form a set, which is a separator of 2 and 6. And it is minimal because if any of the 4 vertices of that set were removed, 2 and 6 would be connected through any of the 4 colored paths. And we can see that that separator is not contained in any neighborhood. So if we want the separators, the minimal separators, to be contained in a neighborhood, we have to be true that some additional conditions have to be satisfied. And what we could prove is that in a dually chordal graph G, every minimal vertex separator is contained in the neighborhood of a vertex if and only if each chordal cycle of the graph is in the neighborhood of some vertex. So if we consider again the graph of the example, we can see that 1, 2, 3, 4, 5, and 6 induce a chordal cycle, and no vertex is adjacent to the 6. Now I am going to speak a bit about the characterizations of dually chordal graphs appearing in the paper. it has been previously mentioned that dually chordal graphs can be characterized by the existence of compatible trees such that cliques and neighborhoods induce subtrees. But that is not the only thing that we can say about compatible trees, because it can be proved that minimal vertex separators also induce subtrees. And conversely, if we have a spanning tree such that any minimal vertex separator induces a subtree, we can say that that tree is compatible, leading to the first characterization, which says that T is dually chordal if and only if there exists a tree T spanning such that every minimal vertex separator induces a subtree. This could be in turn used to get a second characterization. One first conclusion of this is that minimal vertex separator induce connected subgraphs as they induce subtrees of compatible trees. By the same reason, by the fact that subtrees of a tree form a Heli family, we can also conclude that f of t is Heli. And as the intersection graph of a family of subtrees of a tree is chordal, we can also conclude that L of S of T is chordal. Then we have three necessary conditions for a graph to be dually chordal, but what we can prove is that in fact these three conditions are also sufficient. So the second characterization is that she is dually chordal if and only if each minimal separator induces a connected subgraph, S of T is Heli, and L of S of G is chordal. From what we said before, we need to prove it the way up to complete the proof. But before speaking of the proof, I would like to show with an example that none of the three conditions is redundant, in the sense that the three conditions are necessary to get an if and only if statement. In this picture, the colors indicate the subgraph that minimal separators induce. And each one of these graphs satisfies two of the three conditions, but fail to satisfy the remaining one. For example, in the first, S of T fails to be Heli. In the second, L of S of T fails to be chordal. And in the third, some minimal separators induce disconnected subgraphs like the red one. Well, and the proof relies on a property that has been known for some tens of years, that if a family of sets is Heli and its intersection graph is chordal, then it can be represented as a family of subtrees of a tree. That will allow to take a tree T whose vertices are the vertices of G, and such that any minimal vertex separator of G induces a subtree in T. But nothing ensures that this tree is a spanning tree for G. So we will ask for the additional condition that the summation of the distances in G between vertices adjacent in the tree is as small as possible. This way, the tree T turns out to be a compatible tree, a spanning tree. In fact, if it were not a spanning tree, we could take an edge of the tree whose vertices are not adjacent in G, we could remove it, and we could use the hypothesis to get and add a new edge conveniently chosen to get a new tree such that the minimal vertex separators also induce subtrees, but this time with a smaller value of the summation described before, contradicting the way T was chosen. Then this is a spanning tree with each minimal vertex separator inducing a subtree. And by the first characterization, then the graph has to be dually chordal, completing the proof. This property sounds very similar to the one which said that the graph is dually chordal if and only if G was heavy and K of G was chordal. But that characterization did not meet a third condition of connectedness because please naturally, if you connected subgraphs, whatever the graph is, dually chordal or not. So, as a summary of all what said, we can say that we were not only fortunate to learn some properties about separators of dually chordal graphs, but we also became aware that they are very connected to the theory that was previously developed and which involved trees of dually chordal graphs. Thank you.
Bueno, ahora cómo se apaga esto. ¡Bravo, Pablo!
Ya veo que no filmó.